In the last lecture, we discussed various aspects of light emitting diode. We had seen that for optical communication, two sources could be possible. Both are semiconductor based. One is light emitting diode and other one is the injection laser diode. We saw the limitations of LED, that LED has large spectral width and also it has a very low efficiency. Because of that, it cannot be used for long distance communication. So, now in the following lectures, we investigate the operation of a laser and also see how laser is superior compared to LED from the view of optical communication. As soon as we say a word laser, we think of coherent radiation. However, up till now, whenever we have discussed the optical communication aspects, we never made a case for coherent radiation. We have seen certain characteristics which are required in the source for optical communication. However, nowhere explicitly we have seen that the coherency in the light is required for optical communication. One can ask then question, why the laser, which is supposed to be a coherent source, is more suited for optical communication. And this question one can understand better if we understand properly the meaning of coherency, and then we see what are the characteristics which are embedded inside the coherency, which are suitable for long distance optical communication, and then we can make a case for laser as a source for long distance communication. So, in this case essentially we are going to talk about the basics of laser. First we will talk in general the principles of laser, and then we will go specifically to the semiconductor lasers. As we all know, the laser is a short form of light amplification by stimulated emission of radiation. So, firstly one should note that the laser is not an optical source. Laser is an amplifier. When I compare this with LED, the LED is an optical source. So, you have electrical energy, you give to LED, it gives you the light out. Whereas, when we go to laser, principally laser is an amplifier, and every amplifier essentially requires an input signal which can be amplified by this device. So, in principle essentially laser requires some input signal which can be amplified and you get a large optical output. However, when we are investigating laser here, we are interested in an optical source. So, we will see later that first we investigate the characteristics of laser as an amplifier, then by giving proper feedback an amplifier can be converted into an oscillator which becomes an optical source. So, before we get into various aspects of laser, first let us understand the meaning of coherency and how the parameters which are related to coherency affect the communication on optical fiber. So, coherency, there are two types of coherencies which you see in light. One is what is called the temporal coherency, that means coherency is a function of time, and other one is what is called the spatial coherency, that means in space the radiation is coherent. Now, if you consider light as a function of time and space, so you are having a light as an electromagnetic wave which is moving in space. So, if I look in the space as a function of time, you will be having certain electric field which will be varying in time, it will be also varying in space. What one can then do is one can ask, what is the behavior of this electric field or the amplitude of this signal as a function of time, and what is the behavior of this signal in space in a plane perpendicular to the direction of this light propagation. So, when I try to capture the characteristics of this as a function of time, that is what is called the temporal coherency, whereas when I see how the signal is behaving in a plane perpendicular to direction of propagation of this light, that is captured by this quantity what is called the spatial coherency. So, if I assume that the electric field, let us say, is varying as a function of time and it is having certain amplitude A, then I can define what is called the temporal coherence function, which is given by R of tau, where time is integrated from minus infinity to infinity, at A conjugate t minus tau dt, where tau is the parameter which is the delay parameter. So, what that means is, if you have a arbitrary time function, you just take the sample points. So, I have a certain function which is like this. I consider some point here at some time t, and I consider another point here which is at t minus tau, where the difference in time is tau. I take the product of these two amplitude values and I take all possible pairs which are separated by distance tau from minus infinity to plus infinity, and if I take their sum, that is the quantity which will be this quantity R of tau. So, what R of tau essentially tells you is that how a particular point on this waveform is correlated with another point on the waveform which is separated by a time tau. So, as one can see very easily, if this tau is very small, which is somewhere here, then the 2 points are very well correlated, because whatever is happening at this point, more or less same thing will be happening in the neighboring point also. Whereas, if I consider a point which is very far away, then it is possible when this signal is positive, this signal may be negative, and if I consider all possible pairs, you will see that sometime you will have this positive, this negative, whereas these two both could be positive as for same distance, and so on. So, what we find is that if we consider a typical signal which is varying like this, if tau is very small, then the correlation is large, that means the value of this R of tau is large, whereas as the tau increases, essentially this quantity, the correlation decreases. So, that is what essentially is shown here, that if I take the plot of this quantity R of tau as a function of tau, then typically we get a behavior which will look like that. So, when tau is equal to 0, you get the maximum, and normalize, this function is normalized to 1. So, you say that the correlation is 1, and as the time increases, then this function drops. That means the 2 points on the wave function, they become more and more uncorrelated. So, this function typically, the correlation function which we have, typically has a peak at tau equal to 0, and then it drops as tau increases. One can ask then this question, what is the use of this temporal coherence function? And one can show that if you calculate the spectral power density of this signal here, then the spectral power density is related to this coherence function through a Fourier transform relationship. So, if I take this quantity R of tau and take its Fourier transform, then I get the spectral distribution of the radiation. So, typically if I have the temporal coherence function which is like this, the Fourier transform of that would look something like this. So, here this is the plot of power as a function of frequency for this radiation. So, we can measure the effective width of this function, and that is what is called the bandwidth of the signal, Whereas if I measure the effective width of this coherence function, we call that as the coherence time, which is denoted by T coherence. So in time domain, if I capture the characteristic of this radiation, then it can be captured in the form of this tau coherence, which is the effective period or effective time over which the radiation will be correlated or will be coherent. If I go to the spectral domain, then this is the frequency range over which the power is more or less confined. And what one can show is that this tau coherence is approximately 1 upon bandwidth. So if bandwidth is small, then we have a tau coherence which is very large, and if the bandwidth is large, then the tau coherence is very, very small. So if we consider the extreme cases of these two things, if I consider the tau coherence 0, that means if I plot this r of tau as a function of tau, and if this quantity is a delta function, what that means is that the signal is varying in such a way that every point is correlated with itself, but the neighboring point, no matter how small away it is, the correlation is going to be 0. If this function becomes a delta function, then its spectral density, which is the Fourier transform of this, becomes a constant function. So this is S of omega. So this will become a uniform function. Or in other words, you will get a spectral width which will be infinite if the correlation function becomes a delta function. So in this case, your tau coherence is 0 and your bandwidth is infinite. If we take exactly opposite case, that the tau coherence is infinite, spread like this. So this is r of tau. What that means is that the radiation is now completely coherent in time. You know the value of the signal at a particular point, and with 100% confidence you can predict the signal at any other time. Then the correlation function will be constant, and then the spectral density for this, if you calculate, that will be a Fourier transform of this, which will be a delta function. So this is omega. Now a delta function frequency spectrum essentially represents a purely sinusoidal wave. So what we find is, if we consider a sinusoidal wave, then its correlation is perfect, its correlation function is constant, and its coherence time is infinite. So in this case, your tau coherence is infinite and your bandwidth is 0. In practice, we neither have this situation nor have this situation. So we have a certain bandwidth and we have a certain coherence time for the radiation. But the important thing to note is that they have inverse relationships. So higher the correlation in the radiation means tau coherence is small, that means the bandwidth is large. So if this quantity is small, then the bandwidth will be large. If this quantity is large, that means you will be able to predict the signal over very long distance. The bandwidth will be very, very small. So now you can ask a question, why you require actually the coherency into your radiation? And what we say is that since the dispersion is related to the spectral width of the source, we have seen that the intramodal dispersion or chromatic dispersion is directly proportional to the spectral width. larger the spectral width, worse will be the source for optical communication. So, for a good source, the spectral width should be as small as possible. Or in other words, this bandwidth should be as small as possible, which in turn means that the tau coherence should be as large as possible, or my radiation should be temporally coherent. So, now it makes sense why we are looking for coherency. So, when we say that we are in need of temporal coherency, indirectly we are saying we are looking for an optical source which has a very narrow spectral width, and that is the desirable feature because that has a direct bearing on the dispersion. So, here we conclude that we are looking for temporal coherency because that is the one which guarantees you the less dispersion on the optical fibers. The next thing is the spatial coherency. That do we require spatial coherency in the radiation? So, let us ask what spatial coherency means. So, let us say if I have a electromagnetic wave which is traveling, the wave is traveling in this direction, and this is the plane which is perpendicular to the direction of propagation. I have a variation as a function of time which is not very systematic, some randomly varying function is there. So, if I calculate the correlation between this point and this point, the temporal coherence in this signal is very small because this function is varying more like randomly as a function of time. But if I ask what is the relationship between different points in the plane perpendicular to direction of propagation, and you will see that when this point is passing through maximum, this also is doing same thing, this also is doing same thing, this also is doing same thing. Though this point is not doing same thing what this point is doing, so these 2 points are not very well correlated, but these points are very well correlated. So, if I define now the spatial coherence function similar to what we have done as a temporal coherence function, that R of lambda is again integral a of x, a conjugate x minus lambda dx, where lambda now is a separation in the plane perpendicular to the direction of propagation. I will get now a coherence function which will be similar to what we saw for the temporal variation. Only thing in this case, you may have coherence function which may be 2 dimensional, but let us for simplicity assume that I am just plotting this function as a function of x. Now, the radiation is moving in this direction. So, let us say if I consider any other direction at an angle theta with respect to this one, what one can show is that the power radiation pattern for this radiation has a Fourier transform relationship with the spatial coherence function. So, again we can use the same properties which we saw earlier. If this quantity is uniform, that means all the points are perfectly correlated from minus infinity to infinity in this plane, then the Fourier transform of that would give me a radiation pattern which will be delta function. So, that will correspond to the propagation of radiation precisely in that direction, which is theta equal to 0. Whereas, if I have this function which has a finite width, we will have also finite width for the radiation pattern. So, if I am having a function which is partially coherent in a plane perpendicular to the direction of propagation, it essentially means that the radiation is not focused in this direction, but it goes over a finite angle, finite angular zone. Now, if you recall, we had seen when we were discussing LED that the major loss of efficiency takes place because the photons, when they are born, they can go in any arbitrary direction, and only those photons which are within the critical angle cone can escape from the device. If by means of some mechanism, if you can create the photons only within the critical angle cone, then most of the photons will come out now, because they are lying within the critical angle cone. So, if I make sure when the photon is born, it travels only in the direction which is within the critical angle cone, you will see that substantial improvement in the efficiency will take place. Similarly, if you have a very focused radiation or beaming radiation, then it can be launched very efficiently inside the optical fiber, because again this will lie within the numerical aperture cone of the optical fiber. So, from the efficiency point of view, essentially we are needing a highly directional radiation pattern. We are looking for a pattern which will look like that, and if that happens, then the efficiency of light generation will be high. And since the width of this is related to the spatial coherency, smaller will be this width if the spatially coherent radiation is there. We want the spatial coherency in the source. So, what we now find is that for increasing the bandwidth or for smaller dispersion, we require temporal coherency in the source, because that gives me the narrower bandwidth. On the other hand, if I have a spatial coherency in the source, then it gives highly directional radiation, and that in turn increases the efficiency of the device. So, now it is very clear that when we are looking for a laser, the laser gives a radiation which is coherent, and it is coherent spatially as well as temporally, and this coherency is needed because indirectly it gives parameters which are desirable for high speed optical communication. So, now let us say if I have to now define the coherency between two photons, what is the precise definition now is there for the coherency? So, we say that the two photons are coherent if and only if they have same energy, and since the energy is equal to h into frequency, and h is the Planck's constant, it should have same frequency, they should have same phase, the photon should be moving in the same direction. As we saw for the spatial coherency, all the photons moving in same direction, the beam is highly directional. So, this comes from the spatial coherency, this comes from the temporal coherency. But now, if you look at the photon as an electromagnetic wave, then you have the vector nature of light. That means, the electromagnetic wave has electric and magnetic fields, and then electric field has different behavior as a function of time, which is characterized by this parameter what is called the polarization. So, it is possible that the two photons are moving in the same direction. So, they have the same momentum vector, they have the same frequency, but if the electric fields are oriented perpendicular to each other, these two photons will not show any interference. So, coherency or coherent behavior of light can be seen through the interference phenomena, and for that to take place, not only these quantities should be same, but the polarization of the photon also should be same. Now, how do we define the polarization of a photon? It is the polarization of that electromagnetic wave to which this photon belongs. So, if I take an electromagnetic wave or light source, I can find out what is the state of polarization for that light beam. The polarization state of a photon which is taken from that light beam is the same as that of the light beam. So then we say that two photons are coherent if these three quantities, energy, momentum and polarization, are same. So essentially coherency can be defined by a triplet, which is energy, momentum vector and the state of polarization. So we can say the two photons will be completely coherent if the triplet is same for the two photons. With this understanding of coherency, now we can go to the very basic processes which take place inside a material, and then from there we try to establish the coherent radiation, conditions under which the coherent radiation would take place, which will essentially give the foundation of the laser. So let us consider any material and let us consider only a simple system of two energy levels. So let us say we have these two energy levels, and let us say this energy level is given by E1, this energy level is given by E2. This is the lower energy level and this is the higher energy level. Difference of these two energy level, E2 minus E1, is, let us say, is denoted by E photon. Now, because of thermal excitation, the electrons occupy different energy levels. So you have a density of electrons in this energy level and you have a density of electrons in this energy level. So if I consider a general material, then the density of electrons at different energy levels are related, and that is given by the Boltzmann distribution. So if I say that the electron density in this level is given by N1 and at this level is given by N2, then by Boltzmann distribution N1 upon N2 will be e to the power h nu upon kT, where h nu is the energy difference in these two levels. So h nu in this case is E photons. So this quantity is h into nu, where h is the Planck's constant and nu is the frequency of the photon. K is the Boltzmann constant and T is the absolute temperature. So firstly, what we note here is that the density exponentially decreases as we go to the higher energy levels, because the N2 upon N1 will be e to the power minus h nu by kT. So one can just take typical numbers and try to see, if I calculate at room temperature some typical energy levels, what is the ratio of the electron density at energy level E1 and energy level E2. So let us say I take the room temperature, so T is 300 K, and let us say this quantity here nu, that corresponds to a wavelength which is about 0.7 micrometer. So let us say we have lambda which is 0.7 micrometer. Now this energy difference E2 minus E1, that is h into f or h into nu, which is h into velocity of light divided by lambda. I can substitute now the values here. So for h, which is 6.6 into 10 to the power minus 34 into velocity of light, which is 3 into 10 to the power 8 divided by the wavelength lambda, which is 0.7 into 10 to the power minus 6. So, approximately this number would be 3 into 10 to the power minus 19 watts a second. We can calculate the thermal energy, which is kT. The Boltzmann constant is 1.38 into 10 to the power minus 23 multiplied by temperature, which is 300. So, that is approximately equal to 4 into 10 to the power minus 21 watts a second. So, if I get this quantity E2 minus E1 by kT, so this is which is nothing but EPH. So, if I get this quantity EPH by kT, this will be typically of the order of about 100, or the N2 by N1, which is equal to, I am taking N2 by N1 here, so e to the power minus E photon divided by kT. So, this will be e to the power minus E photon by kT, which is of the order of e to the power minus 100. So, this number is typically of the order of about 10 to the power minus 32. So, what that means is that if we consider the energy levels which have energy difference correspond to about 0.7 micrometer, then the ratio of the electron density in the upper level to the lower level is 10 to the power minus 32. That means, this level is practically empty compared to the electron density in this level. Most of the electrons are going to be in this level, and there are hardly any electrons you will find in the upper level if the energy density or energy difference is of the order of this quantity, which corresponds to about 0.7 micrometer. This is a natural situation. So, what we find is that if I consider a system at thermal equilibrium, which has a temperature T, then the electron density at the upper energy level will be negligibly small compared to the electron density at the lower energy level. Now, let us say in general we are having now the electrons which are lying at the upper energy level and they are lying in the lower energy level. Now, if the electron is lying in the upper energy level, it has a tendency to relax to the lowest energy level state. So, if the electron was in the upper energy level, we say the electron is in excited state. When it comes down to the lower energy level, we say the electron is relaxed to the ground state. So, the two states which we have shown here, we can say this is the ground state and this is the excited state. So, since we are having now the distribution of electrons, there will be some electrons which will be in the excited state because of thermal excitation, and large number of electrons will be there on the ground state. However, what we are saying is, if the electron is in the excited state, it has a tendency to relax to the ground state, and when that happens, essentially the energy is shaded away, and this energy will be emitted in the form of photon, of energy, which is EPH, which is E2 minus E1. So, what we say is that if the electron is in the excited state, which is here, then naturally it has a tendency to come down to the ground state or relax to the ground state, and when this transition takes place, a photon is released in this process. So, let us say this photon is released in this process. Now, since this process does not require anything else, it is just that since the electron is there in excited state and it has a natural tendency to relax to the lower energy state, this process is what is called the spontaneous process. And whenever spontaneous process takes place, a photon is released of a frequency which is h into f, where hf is nothing but the energy difference between these two levels. So, as we have called, this is E2 and this is E1. This quantity hf will be E2 minus E1. This is one process which takes place inside the material. The other process which you observe is that suppose we take a material and shine light on the material. When the light propagates through the material, the intensity of the light reduces. What that means is that the part of the energy of the light beam has been absorbed inside the material. What does this energy do? This energy essentially excites the electrons from the ground state to the excited state. So, if the photon was incident on this system and if the electron was there on the ground state, then this process, what is called the absorption process, will take away the energy from the photon, give the energy to the electron, and the electron will get excited to the higher energy state, and the photon will be lost. This process we always see in nature, because we have seen always when the light beam passes through a material, it attenuates. So, number of photons are lost. The energy of these photons is given to the electrons and electrons are excited. So, internally the material is excited because the electrons have gone to the higher energy state and the photons are lost. Also, when we consider a normal material, we also see that it gives you the black body radiation. So, you always see some light or electromagnetic waves coming out of a body. So, even this phenomena in some sense has been observed. You can see that this phenomena would exist. What is proposed now is that in addition to these two phenomena, which one can observe very easily in nature, there is also a process which is the force process. And that process is, if you are having an electron in the excited state here, and if the photon is incident onto this system, then this photon may force this electron to jump down, and when this jumping takes place, it will release a photon. So, this original photon will force this electron to jump and emit another photon. So, this process which we are talking about is not taking place on its own by electron, it is a force process by photon, and this process we call as the stimulated process. And the postulate was that when this force process takes place, that time the photon which is released now, additional photon, since it is now completely under the influence of the original photon, the properties of the new photons are exactly identical to the original photon. Or said in terms of coherency, the two photons now which we have, they are completely coherent photons. And we have seen what complete coherency means. They are spatially coherent and they are temporally coherent, and they have the same polarization. So, the two photons now will be traveling together in the same direction, they will have the same frequency and they will have the same polarization. So, this process now is with the presence of a photon. This process is with the presence of a photon. So, when the photon or light beam is incident on a material, two processes might take place. One is the photon may get lost and the electron can get excited, or the photon may force the electron, if it is in the excited states, to jump down and release another photon which is completely coherent with the original photon. Now, this process is rather a multiplicative process, because if you are having one photon is given 2, the 2, if you are having more electrons present here, they will pull down more photons and so on. So, you have a process which grows very rapidly, the stimulated process. What one can do is, now one can define some quantitative parameters to define these processes, and these are defined by the transition probabilities, which are called the Einstein coefficients. So, the process which does not depend upon the photon, that is given by the coefficient which is called A21, and the process which takes place in the presence of photon, that coefficient is denoted by B. So, this process which is taking electron up from energy level 1 to 2, that is coefficient is given by B12, and the stimulated process, the coefficient is given by B21. So, now we can say that if you are having an electron density here, the rate of electron transition downwards by its own nature, by spontaneous nature, will be proportional to the number of electrons present in the upper energy level. So, now we can write down essentially the equations for these processes. So, we say if the electron density in the upper level is N2 and the electron density in the lower level is N1, then we can write down the equations for three processes as follows. So, first take spontaneous process. So, here the rate of electron transition downwards or rate of depletion of electrons in the upper level, which will be given by minus dN2 by dt, that will be proportional to N2, the electron density in the upper level, and the proportionality constant will be this quantity A21. So, we can write the equation minus dN2 by dt, rate of change of electrons in the upper level or decrease of electrons per unit time in the upper level, that will be equal to A21 into N2. We can solve this equation, and the simple solution for this will be N2 as a function of time, that will be N2 at t equal to 0 e to the power minus A21 into t. If we define a parameter, what is called the lifetime of the electron in the upper level, and call that lifetime as the spontaneous lifetime, then this quantity A21 will be nothing but 1 upon the spontaneous lifetime. So, we can define the quantity what is called spontaneous lifetime, tau spontaneous, and that is equal to 1 upon A21. So, this quantity here, density of electrons in the upper state will be N2 at t equal to 0 to e to the power minus t upon tau spontaneous. So, what that means is that if the electrons are transported to the upper energy level, then naturally the electrons will have a tendency to decay, and this decay will be exponential with a characteristic lifetime which will be tau spontaneous. So, this process is a very straightforward process. Similarly, we can write down the equations now for the other two processes, and since the other two processes depend upon the photon present there. So, let us say there is a photon flux density which is given by a rho of nu. So, what we are saying, if we are having a material like this, you are having a photon flux which here, which is as a function of rho of f, where f is the frequency. So, now we can write down the absorption process. Where electrons are taken from the ground state to the upper state, and now the rate of change of the electron density in this level will be proportional to this quantity, will be proportional to what is this quantity or density here in the lower state, and is also proportional to the photon flux which is rho of f. So, we can write here this is minus dN1 by dt, that will be equal to B12 rho of f into N1. Similarly, we can write down the stimulated process, where the transition is going to be downwards. Again, the rate of change of electrons in the upper level will be proportional to N2, will be proportional to the photon flux density, and the proportionality constant will be B21. So, we can get here minus dN2 by dt, that will be equal to B21 rho of f into N2. So, now we have got three processes simultaneously operating inside the material. There are two processes which are bringing the electrons down from the excited state to the ground state, and then there is one process which is upward process, which is taking electrons up from the ground state to the excited state. So, in thermal equilibrium, since the number of electrons are not changing either at the ground state or in the excited state, the total downward transition must be completely balanced by the upward transition. So, we can essentially write down the balance equation from here, which says that the upward transitions are equal to downward transitions. So, we can have these two things equal to this. So, we can get from here essentially A21 N2 plus B21 rho of f N2, that is equal to B12 rho of f to N1. So, these two are downward transition, this is the upward transition, and in the equilibrium these transitions are completely balanced. So, neither electron density is changing in the upper energy level nor it is changing in the lower energy level. If we rearrange this, we can find out what is the net photon flux coming out of the material. So, if I simply rearrange this and substitute into this, we can get the net photon flux which will be coming out of this rho of f, that will be equal to A to 1 and 2 divided by B12 and 1 minus B21 and 2. By taking this B21 and 2 common from here, that will be equal to A 21 by B21 divided by B12 upon B21 N1 upon N2 minus 1. So, what this expression essentially is giving you, that if all the three processes, spontaneous emission, absorption and stimulated emission, take place simultaneously inside the material, then there is a net photon flux from the system, and that photon flux density is given by this. What one can do now is that since the system is at thermal equilibrium, this photon flux must be identical to the black body radiation, because if the body is at some temperature T, it gives you the radiation. So, if I now take the black body radiation expression and compare this expression with that, then we can deduce some relationship between these quantities A21, B21, A12, B and B12. These quantities now A21, B21 and B12 are called the Einstein's coefficients, because he was the one first who investigated this problem and then tried to establish the relationship between these quantities. So, in the following lecture, what we will do is, we will take this expression of the photon flux density, compare this expression for the photon flux density from a black body radiation, and then deduce some very important conclusions.